Our picture of chemical reactions up to this point has been that we start off with our reactants and generate products. And we can use our balanced equation and the stoichiometric coefficients to figure out how much product we get for how much reactant. Well, consider that some reactions might take millions of years to complete. We probably aren't going to wait millions of years for them to do so. So we're going to interrupt them sometimes before they finish. In that case, we're not going to get the stoichiometric amount of products. In general, there's something interesting happening in between our reactants and our products. And if we understand some more about what's happening, we understand more about our reaction and can model it more effectively. So what's happening is that molecules are bouncing together. And sometimes they react, sometimes they don't. So these are actually statistical events. And how many reactions that we get and how long it takes to fully react all of our reactant is going to depend on how often our molecules collide, which is the collision frequency. It's going to depend on the shape and the orientation of the molecules. And it's also going to depend on their energy when they come together. Well, it's probably clear that if we have our molecules collide more often, that they're going to react more often. So if we have very few molecules compared to having a whole slew of molecules in high density, then in the second case, we have more opportunities to react. So we're going to observe a higher reaction rate. So this second scenario, that represents high pressure for a gas or high concentration for a gas or aqueous solution. Now we can also bring more molecules into contact by agitating our solution, especially when they're being consumed. That will introduce new molecules to where other molecules have reacted already. And temperature will also increase this collision rate because now the molecules are moving faster. This is really the smaller effect that temperature has. The larger effect it has is on the energy of the reactants. So this is why when you add very concentrated acid to water, you get a very vigorous reaction compared to if you add some diluted reaction. You don't notice such a vigorous reaction, even if you have the same number of moles diluted in a larger volume. There are bacteria on the ocean floor that are millions of years old and they take 10,000 years to reproduce. And the situation is that they have a very scant quantity of their essential nutrients that they need for their biological reactions. And so it takes a very long time for them to complete the normal metabolic processes that organisms in more nutrient-rich environments are able to do more rapidly. It also matters a great deal what the molecule looks like. If we have just atoms coming together and reacting, they're spherically symmetric, and so it doesn't really matter what orientation they're in. Probably any time they come together, they're going to react. We have larger molecules. We might have this kind of key lock scenario where the key has to fit inside the lock. And in order for that to happen, it's going to have to be properly oriented to fit inside the lock. And so that can be very unlikely that it's in the exact right orientation. Now, something that can affect this is called a catalyst. This is another substance or structure which helps to mediate these molecules coming together in the right positions. And so those can make these kind of reactions happen much more frequently and therefore much more rapidly. Most reactions which occur are exothermic. So we start out at a high energy state for the reactants, and we go down to a lower energy state for the products. And it's favorable in physical systems to bring them to this lower energy state. So why doesn't this just spontaneously happen? Why don't we just spontaneously move to a more favorable configuration? Well, the reason is because we have to get there. And in order to get there, we have to break bonds and flex bonds and form new bonds. And in the process, we encounter very high energy configurations called intermediates. And we have to supply that energy to get to the intermediate state before we can recoup the energy difference between the reactants and the product states. And so this is what prevents everything that's reactive from spontaneously reacting. And if we want to affect this, there are catalysts. What catalysts do is they provide a new pathway which is lower in energy. And so that will make this easier. We can also affect this by increasing the temperature, which will increase the energy of the reactant molecules, meaning that more of them are going to have enough energy to navigate the hurdle of the transition state and make it to the product side. Reaction rates, as you might imagine, are something that we want to keep track of mathematically. So we're going to formally define, first of all, the rate of change in concentration for particular reactants. So we're going to take the difference between the second concentration and the starting concentration, and the difference between the second time and the initial time, and that ratio is our rate of change in concentration for the reactant. We're also going to define reaction rate. So if we have a general equation, these lowercase letters represent the stoichiometric coefficients, and the uppercase letters represent the substances. Then the reaction rate is defined to be negative 1 over the coefficient times the rate of change in concentration with respect to time for our reactants, and positive 1 over the coefficient times the change in concentration with respect to time for the products. Now, the reason that these signs and subscripts are here is to make sure that these are all equal to each other. What we would like is we would like to be able to measure this substance, or this substance, or this substance, or this substance, and get the same answer for our reaction rate. Now, if we produce twice as much product as we consume of reactant, then we would get twice the number here for our change in concentration. So if we divide by 2, that will make sure that this quantity is equal to this quantity. The other thing we have to fix is that since reactants are being consumed and products are being produced, the reactants are going to need some minus signs thrown on them in order to make sure that they come out positive in the same way the products do. Now note that there's something inconvenient about using this definition. We're going to have to take at least 2 different concentration measurements to get that interval between the starting concentration and the ending concentration. Since this applies to an interval, we're just going to get an average reaction rate over the times in between what we measure. So if our reaction is changing in reaction rate very quickly, if it very rapidly completes, then probably that average measure is not going to be useful if it's even possible to obtain experimentally. Say we have this reaction where 4 ammonias react with 3 oxygens to produce 2 nitrogens and 6 waters. We take some concentration data using our sensors. We find at the very beginning there is 0.63 molar concentration of oxygen in our chamber, and 15 seconds later there's 0.21 molar concentration. So what is the reaction rate for this reaction based on our measurements? Well, our equation was that the rate is equal to negative for the reactants, 1 over the stoichiometric coefficient times the change in concentration with respect to time, or positive for the products. So let's go ahead and just plug in these quantities here. So for oxygen, we have a stoichiometric coefficient of 3. So we'll put 1 over 3. And it's a reactant, so that's going to be negative. And then we'll take the change in concentration, which is going to be the second concentration, minus the first concentration, divided by the change in time, which will be the second time minus the initial time. Now note that this will wind up being negative here, which will cancel out the negative factor that we've introduced. And that's good because our rate should always be positive for a reaction. So this comes out to 0.0093 molars per second. Let's ask another question involving that equation. What is the range and change in concentration of the ammonia? Now, the nice thing about this equation is that if we know information about any one substance, it's going to let us convert that to information about any other substance. So this, again, was our reaction. 4 ammonias and 3 O2s react to give us our nitrogen and water. So for the ammonia, plugging into our equation, since we have a coefficient of 4 here, we'll put 1 over 4. So reactant, we'll put a minus sign, times the change in concentration with respect to time, has to be equal to what we wrote down for oxygen. It's another way of expressing our reaction rate, which we just calculated was 0.0093 molars per second. So just multiply this by this negative 4 to get this by itself. And we get negative 0.037 molars per second. Now note that for changes in reactant concentration, these can definitely be negative. This minus sign means that it's decreasing in concentration. But our reaction rates for the overall reaction, we define to always be positive. Now sometimes, for some reactions, we can come up with our rate of reaction by another means. Our rate of reaction can be written as a constant times the concentrations of the reactants raised to some power. Now the constant we're going to measure experimentally. Same thing for these powers. These powers, they might be integers, they could be fractions, or they might even be irrational numbers. In many cases, many of the problems that we work, we're going to find that they are integers, but not always. Now the nice thing about this equation versus our other equation is that this requires only one measurement of the concentrations. Our definition of a reaction rate, we had to measure at least twice over an interval. And this is going to give the exact reaction rate at that specific concentration. It's not the average over an interval. Now as mentioned, these must be determined experimentally. And in order to discuss what rate law we've come up with, we're going to define the order of the reaction to be the sum of these exponents. So for example, here we have rates equal to the rate constant times the concentration of iron and the concentration of oxygen squared. So the order for this reaction is going to be the 1, which is implied here, plus the 2, which is written explicitly. The overall order for this reaction is going to be third order. Well, how are we going to find these rate laws for our reactions? We're going to have to use experimental data to do so. Our experimental data is going to consist of the different reaction rates at different measured concentrations. And once we have that information, we can use algebra in order to determine the equation that should go along with it. So the first thing that we're going to do, we're going to write a series of equations, plugging in our data, our specific rates and our specific concentration values. We're going to leave k, m, and n just as k, m, and n because we don't know them yet. Now remember in algebra, if we have as many equations as we have unknowns, then we can figure out the value of the unknowns. So we're going to need at least 3 equations for k, m, and n. Once we have those equations, then we can solve for k, m, and n. We could do so by substitution. A trick to make this easy is, since the left and the right sides are equal, we can always do to the left side whatever we do to the right side, which includes dividing by equal quantities. So for one of these, say our rate 2 equation, I can go ahead and divide by the rate 1 from the rate 1 equation, and then divide by the right side of the equation. And since this and this are equal, and that will maintain this equality. And the reason I would do that is because that's going to make these k's cancel. So I have successfully eliminated one of my 3 unknowns. And if I'm really lucky here, if I have concentration data for A1 and A2 where they're the same concentration and it's only the concentration of B that's varying, then that will make it so that A1 cancels out. And then I'll just have this number, whatever it is equal to concentration of B to some power. And that will make it really easy to find what that n should be. Now, once we've done that, we can solve for m or n. So let's say we take the ratio of our rate, so we get 26.9, and we've managed to set it up so that the k's and the B concentrations cancel. So we have our concentration for A at one experiment divided by our concentration for A in another experiment, both raised to the power of m. Our rule for exponents is that we can go ahead and perform that division first, and raise all of that to m, since both of these are raised to the nth power. And here I've plugged in concentrations of 6m and 2m, which comes out to 3. So we have 3 to the m is equal to 26.9. Now, because these are often integer values, then we can use a trick here. So m must be equal to 3, because I recognize that 26.9 is very close to 27, which is 3 to the third power. Now we do the same thing in order to find our missing n or m value. And once we have done that, then we can pick any of our sets of data for rate 1, rate 2, rate 3, etc. And we can go ahead and plug in what we found for m and n in order to find k. Now, actually, it would be best if we did this for all of our sets of data, found all the k's for rate 1, rate 2, rate 3, etc., and took their average. But frequently, for what we are doing right now, we're going to be satisfied with finding k for just one set of data. Well, let's say that we have this reaction here where we have CH3Cl, that's chloromethane, reacting with diatomic chlorine gas, and produces carbon tetrachloride and hydrochloric acid as a gas. We do some experiments. Remember, we're going to need to perform at least 3 experiments to find our 3 variables, k, m, and n. And so we do one experiment where we have a 0.1 concentration of our chloromethane and a 0.1 concentration of our chlorine. We measure the reaction rate, and it turns out to be 0.04 molars per second. We do our remaining 2 experiments. Now, using this data, what is the rate law for the reaction? Well, the first thing that we want to do is we want to take all these pieces of data and turn them into equations. So, for example, for this first line, I'll plug in the concentration for the chloromethane, and I will plug in the concentration for the chlorine, and I will plug in the reaction rate to the general equation, and then I'll do the same thing for the second line, and again for the third line. So now I've turned my 3 experiments into 3 algebraic equations. Now what remains is just to use algebra to find k, m, and n. So the way we're going to do this, we'll go ahead and use our trick. So we're going to divide 2 of these equations. And we set this up. First of all, k is definitely going to disappear when we do this, because it appears in numerator and denominator. And we specifically chosen 2 pieces of data that had the same factor for n. So 0.1 to the n and 0.1 to the n. Since these are the same, they're going to cancel out as well. And so then m is going to be the only quantity that we have to solve for. Now 0.2 over 0.1, both raised to the m. Our rule for exponents allows us to shift the 0.2 and the 0.1 together, both raised to the power of m. And then that's going to be equal to our rate 2 divided by our rate 1. So that's the 0.79 divided by the 0.4. Now 0.2 divided by 0.1, that's just 2 to the power of m. And the value of this is 1.975, which is very close to 2. So we'll just go ahead and call that 2. And so what's m have to be equal to? Well, 2 to the power of 1 would be equal to 2. So we recognize that m must be equal to 1. Now we need to find n. We're going to use the same strategy that we used to find m. We're just going to use some different rate data. So in this case, I'm going to use the rate 3 data and the rate 1 data. And the nice thing about this is going to be that the 0.1 molar in the rate 3 is going to divide out with the 0.1 molar in the rate 1. And so that will go away, and k will go away. And we'll just have 0.4 molar to the n divided by 0.1 molar to the n is equal to this ratio over here. And just as a coincidence, this turned out to be the same ratio that we were using before. But you wouldn't always expect it to be the same ratio. Well, 0.4 over 0.1, that's equal to 4. So we have 4 to the n. And this comes out to 1.975, which is about equal to 2. So 4 to the n is equal to 2. What does n have to be equal to? Well, you might recognize that 2 is the square root of 4. Now, another way to write a square root is whatever number to the 1/2 power, or to the 0.5 power. If you punch in 4 to the 0.5 in your calculator, it should come out to 2. So in this case, n is equal to 1/2. Now we can find k, and the way we're going to find k is we're going to choose any of our pieces of rate data, either rate 1, rate 2, or rate 3, and we're going to plug in what we know for m and what we know for n, and then we'll just solve for the missing value. So in this case, we used the rate 1 data, where the rate was equal to 0.04 molars per second. Now m we know is equal to 1, n is equal to 1/2, and then we're going to have to take this chunk over here and divide it in both sides to get k by itself. So we go ahead and do that. Get 0.04 divided by 0.1 to the first power and 0.1 to the 1/2 power. Now I punch that in, it gets 1.26 for the numerical value. Now a note about the units on these rate constants, they'll come out differently depending on what order of reaction you're dealing with. We want to make sure that the units that we give our constant match the units that we have in our equation. So here we had molars divided by seconds. Another way you can write divided by is just to put a -1 to say that whatever it was belongs in the denominator rather than the numerator. Now the molars is going to be canceled out by this molars right here. And then what will remain is that we're dividing by molars to the 0.5. And so since we're dividing by it, it becomes a minus. So 1.26 molars to the minus 0.5 or 1/2 times seconds to the -1. Now that we have all our information for k, m, and n, we can go ahead and write out the rate law. So our rate constant times the concentration of CH3Cl to the first power. Now 1 you don't have to write in explicitly, although you can. It will just be implied that it's 1 if you don't write anything there. Times the concentration of Cl2 to the 1/2 power. And just a note on the reaction order here. Remember the reaction order is the sum of these exponents. And so here we have m is equal to 1 and n is equal to 0.5. So our reaction order for this rate law is 1.5 altogether. That's certainly a lot of math to write down for finding a rate law. There's a shortcut which can save you a lot of time if you're comfortable with it. If we look at our data and we just recognize that, for example, doubling one concentration doubles the rate, or tripling one concentration triples the rate, then we know that that must be first order. Or if doubling one concentration quadruples the rate, or tripling a concentration results in the rate increasing by a factor of 9, then we would know that it was second order. And so in general, we can have some insight just by looking at the data. Let's look at the example that we had done previously and see if we can use just intuition to figure out most of the rate law without having to actually work out all of those algebraic equations. We know the rate law is going to be of the form rate is equal to K times the concentration of chloromethane to some power times the concentration of chlorine to some power. Now, if I look at my first two experiments here, the concentration in chlorine does not change, so that doesn't have any effect in the change in this rate here. The only thing that matters is the fact that this chloromethane doubles in concentration, and when that happens, my rate looks like it approximately doubles in concentration. So what that tells me is that this reaction is first order in the chloromethane concentration. Well, now we can compare experiment 1 and experiment 3. And in these experiments, the chloromethane concentration is the same. So that doesn't affect this change in reaction rate. Now my chlorine concentration quadruples. And when it quadruples, my rate merely doubles. So that tells me that I have a power to the 1/2 relationship.